All right, welcome everybody. Today we're going to be talking about RAG, and we're going to be learning how you can use Mastra to do a bunch of things with RAG. So thank you all for joining us. If you're watching, if you're in this Zoom, workshop, or if you're watching live on YouTube, LinkedIn, X, you can definitely, please let us know in the chat if you do have questions along the way. You can, if you're in the Zoom, use the Q&A section. That's the best way to get questions answered. We will try to answer some questions along the way, but then also we'll save some time at the end just to try to get through as many questions as we can. And if we can't get through everything, we'll encourage you all to join the Discord and follow up after the event in our Discord with questions. But we'll get through as many as we can. And I will share my screen and we will get started here and talk a little bit about RAG. All right. Are you able to? I don't think you can actually see this. Let me try. For whatever reason, I need to share my whole desktop. So let's do that. All right. All right. I think we're good now. So what's the goal of this workshop? We're going to build RAG applications with Mastra. We're going to learn a lot about RAG concepts and how you can apply those concepts with Mastra. So if you don't know anything about RAG, this will hopefully give you an overview. And if you do know a little bit, hopefully you'll see some practical examples that you can use if you want to use Mastra. So we're going to talk some common RAG concepts, chunking, embedding, retrieval, re-ranking, and then we're going to talk about actually using those within Mastra. So who are we? So I'm here with Nick. He's a founding engineer at Mastra. He was previously a senior software engineer at Netlify, and he's pretty excited about RAG. Please connect with him on X or Twitter, whatever we call it these days. I am one of the founders of Mastra, chief product officer. I was previously in Eng and product at Gatsby and Netlify, and I've been doing open source software for quite a while. And you please connect with me as well. So what is RAG? This is a good kind of high level overview of all the things that are going on when you're thinking about building a RAG system. You have some kind of, it's kind of best to start at the bottom with your kind of knowledge base. You have a bunch of knowledge, a bunch of maybe specific data that your company owns or that you own, and you embed that into some kind of vector store. And then you have this kind of queryable knowledge base. And then you have some kind of input, which is usually a user prompt. You embed that input, that prompt, and you use that for retrieval. And it pulls data from that vector store through some semantic search type capability. And then you maybe do some re-ranking with an LLM, and then you get an output. Now, RAG doesn't just have to be vector stores and semantic search. I think that's a common misperception. I think it is the most common way to do it, but even just regular old search could still be considered RAG. So we'll talk about that a little bit, but just because you use the word RAG doesn't mean it has to be using a vector database. I think that's something that some people equate RAG with vector DBs, and they're correlated, but it's not the only way to do RAG. So what is RAG? It's an AI architecture that combines information retrieval with generative models, LLMs, to enhance the accuracy and depth of AI generated responses. So it's really about getting your external data into the LLM, right? Into the context window of the LLM. And this is one of the ways to get around, context window limitations, especially, if you go back a year ago, context windows were very small. It was critically important to use RAG. Now, some people argue, well, we don't need RAG. Or maybe, some people even, argue that RAG is dead. That's not true in our opinion, but it's a nice thought experiment, but it's not true because even with large context windows, you can still run out of tokens. You can still, even if you do have large context windows, there's still sometimes where you might be able to get better results using RAG. Not always, but you should we like to think of RAG as it's no longer everything is RAG, but RAG is like a tool in your tool belt that you can pull out when you need it for certain applications. So when within RAG, you have this idea of like chunking and pre-processing your data. So you basically take chunking is this taking these large documents or large amounts of data that you have into smaller, more manageable segments or chunks. And then your retrieval actually operates at the chunk level rather than on the entire document. So if you think about if you had let's say a backlog of hundreds of blog posts, you might break those blog posts up based on paragraphs or headings or sentences, however you'd want to chunk that into smaller pieces. And then you would retrieve specific sentences or paragraphs that would then eventually like bubble up to the entire document. One of the challenges, and this is something that you have to learn when you start working with RAG, is you have to balance chunk size. And there's not always a one size fits all solution. If you have too large of chunks, you may have unrelated information, and so your retrieval isn't going to be as good. Too small, you might not have enough context, so it's your retrieval isn't as useful because it's not getting enough of the context. So you typically want to aim for semantically meaningful chunks, but that does vary a bit depending on the types of information that you're actually retrieving. So you may have to spend quite a bit of time testing different chunk sizes in the beginning to see what works best for you and what you're actually trying to accomplish with whatever RAG system you're setting up. You typically want to store additional metadata with each chunk, and then often you may decide to overlap chunks or retrieve neighboring chunks to help improve the context, right? So rather than just getting one chunk, you're getting the surrounding chunks, and that helps you get better context. Another core concept is this idea of embedding models. So an embedding model is a machine learning model that converts text into numerical vector representations. The goal is to capture semantic meaning of words. The idea is the word dog and puppy are maybe semantically close, but if you actually just did a keyword search, they're not the same thing, right? The idea is that by using embedding models, those two words are actually semantically close together. And you know, if you search for puppy, you might get something that says the word dog. And this, again, allows just for semantic retrieval. So there's a number of different retrieval techniques. You have exact matching, which is, you know, you just your keyword-based retrieval. You have semantic search, which is kind of what we've been talking about. You have an embedding-based retrieval. And then you maybe have this hybrid search where you do keyword plus semantic. And a lot of people, when you get into more complex RAG systems, you might be using both. So again, it's not just if you're using semantic search, you're typically using a vector database, but keyword-based search, you might not be, right? So it's not just uh, RAG is not just vector DBs, but it is, you know, maybe a part of your tool set that you use. Another thing that's important, and we typically recommend as one of the first ways to get better results when you're trying to build some kind of RAG pipeline, is the idea of re-ranking. So if you do a vector retrieval, a semantic search, you may get things that it basically gives you a score. And you may want to then look at maybe it's the top 20 or 30 items and then re-rank those to only pull out, you know, the top 5 chunks rather than all of it. Because it's maybe more quick to do a semantic search and get a broad list. And then you can do a more intensive and maybe slower re-ranking on that smaller subset of your chunks rather than trying to do it across the entire data set. So often you'll add a re-ranking step to, you know, you kind of limit it to like a broader set, and then you re-rank and pick just the top handful depending on what you need to pass in. And then there's also this idea of, you know, maybe should do fine tuning because generic embedding and re-ranking models may not achieve high precision and recall in specialized use cases. So our general idea here is it can be useful. You know, we've heard from some people that have gotten better results when they have large data sets and they fine tune embedding models. If you're just getting started, you probably shouldn't be caring about this though, because you should at least be measuring your accuracy before you try to do fine tuning. I mean, you should probably try long context windows, try basic RAG, measure accuracy, and then if you really need, and in some cases you do really need that extra few percentage points of accuracy, then you should start looking at once you have enough data accumulated, maybe you want to do some embedding and re-ranking, or changing either fine tuning, embedding, or re-ranking models. So just keep that in mind. A lot of people, I think, try to get to this too quickly before they really understand all that you can do without it. But it is, at least we've heard from some people that you can get a decent amount of accuracy boost if you do this, but it does come with a cost of time and complexity. And I see some people in the chat saying they maybe can't see the screen. If you are on, we've noticed there's some issues on mobile as well, Zoom sometimes. So if you are on Zoom mobile, maybe it doesn't always work. Sounds like someone says if you pop out the video, you can enlarge it and see it. So hopefully you all can see my screen. All right, so let's talk about Mastra. Mastra is an open source AI agent framework for TypeScript or JavaScript developers. It comes with a bunch of primitives such as agents with tools, memory, and tracing. We have workflows that allow you to do human in the loop, so you can suspend and resume them. It has a simple API where you can call things like .then or .branch to kind of really build out a nice workflow graph. We have evals for tracking and measuring AI output, storage for RAG pipelines, and it's all kind of bundled into a local development playground. The whole idea around Mastra is we want to be opinionated but flexible, so you can get further faster without necessarily feeling like you got locked in. So that's really the design principles that we thought of as we're trying to build Mastra. But we're going to go ahead and get started with RAG, and I'm going to hand it over to Nick, who's going to actually show us the code of how all this stuff works within Mastra. We're going to talk about chunking, embedding, retrieval, re-ranking, and then we'll talk about agent tool usage with RAG. I think Nick maybe even has a workflow example as well. So we got a whole bunch of cool things we're going to show. Nick, I'm going to hand it on over to you.
Yeah, thanks, Shane. I'll share my screen right now. So I got a lot of cool examples to go over with you guys. So I'll start with just going through chunking first, then we'll go through embedding, and then show you guys upserting and some tool usage. So the first thing I want to show, let me make my, and let me know if it's big enough. Can everyone see the code? Just let me know if not.
Yeah, maybe go one
One
more
more
click.
bigger? All right, one more click. Got
But
it.
it looks pretty good. But I think that should be hopefully
Okay.
good enough.
Let me make this smaller. Cool. So the first chunking example I want to show you guys is just the really basic character chunking. Now this one is very simple. It takes basically you specify like a amount of characters you want to chunk on, and it will just split up the whatever document you pass based on that character count. So this is the most simple way to chunk, I would say, where you just give it a text document and then you specify just a hard cap of what you want to chunk, and it'll just split it based on those chunks. So I can show you that right now. To do, if I just run this example. So you see, like, well, first I'll show you the document is the text is this is a simple text document that will be split into chunks based on character count. And if I look at the character chunks that got created from here, let me actually move some stuff around too. You see, like it gets this is a simple text document that will be split into chunks based on character. So it's a very hard limit of 20 characters, and um, this is a good way to chunk if you're starting out, but it's not really. It's just very simple. So if you it doesn't keep into if you want to keep any context or any kind of logical boundaries in your document, it won't do that very well, but if you just want to get started and learn how to chunk in the first place, I think this is a very good way to get that process started. And you can see that the you can see the chunk text afterwards and see how it's split up. But the next one um, is a little more advanced, I would say. It's recursive chunking. Now, recursive chunking is different than character chunking in that try to um, it'll try to keep context within logical boundaries. So when we run this, so we have this code content, which has two different functions. One's a process data and one's transform. And then we have a strategy of recursive. We set a size of 150. So that's how many characters we expect to have in the chunk size. But when we run this example, you'll notice that it's a lot better at keeping just various the different functions together in one chunk. So like we see like function data, function process data is in one chunk, and then we have another chunk for just the transform. This is very good for just making sure that whatever logical boundaries you have set up or want to in place, and it'll make sure that these functions are separated properly and not, and they don't cause any kind of inconsistent chunks where like different functions are in different chunks and it kind of messes with your chunking process. The next one is JSON chunking. Now, JSON chunking is similar to recursive, except this one will keep in mind the nested paths. So for our JSON content right now, we have um, we have a config key, and then inside there we have an API key, and then nested inside there is this object, as well as the features object right here, which is an array of different values. So when we use JSON chunking, we can see that it does we can see that it takes into account the root key. So we see this first content is config API and then we see the endpoint version and timeout object inside there. So we know that in that chunk we can see the path up to the root. So we know that the endpoint object was part of API, which is part of config. And then we can also see in the other chunk, which is config features, and then this array of values, that we're able to map a path back up to the root and be able to reconstruct. We're able to see how we could reconstruct the original content based on what the chunks were created, just by seeing how it's nested down. And this just makes retrieval easier, so it makes it easier to understand how the original content looked. Um, let's move this over here. Cool. Um, the next one I want to show is Markdown chunking. Now, Markdown chunking basically lets you handle Markdown files and lets you split on different headers. So we have this Markdown content, which is a user guide. We have an installation section. It tells you how to install the package. We have a basic usage. We have a configuration section, and then we have an API reference section. But with our strategy, we have a markdown strategy, and then we can define headers that we want to split. So basically, because we have these headers set up, the chunks will be split based on each different kind of header type, and we can add metadata that shows like which I can show you right now. Uh, do that right now. So if you see here, we have these different markdown chunks. So the first chunk is basically this to install the package. Let me um, to install the package, you run that command. But you see in the metadata that we have header one, which is the user guide, and then header two, which is installation. And then the next chunk is here's how to use the main features, which is the basic usage section. And we can see that the headers are set up so that you know exactly where in the document you will retrieve this data from. And the same thing with the configuration. You can go see like header one was user guide, header two was basic usage, and header three was configuration. And you can keep going for this whole document. You can have these kind of sections set up so that once you chunk it, you know exactly which header or which section of the document you can find this original data. So that's our basic chunking examples. Next, I want to go
And
over.
before we switch, there's
Uh,
just a question in the chat that says, what's the best way to set up Mastra to retrieve sources for citations? I think I can probably answer this one, Nick, but definitely jump in if I get anything wrong.
yeah.
But I do think, and Vadim also kind of alluded to this, for citations, you'll often store, where you got the data from in metadata. And so when you retrieve that chunk, you can get the metadata, and then you can, of course, bubble that metadata up to either the front end or the UI and say, this, this piece of content came from this specific URL or source, right? If you wanted to source a citation. So that's a pretty common pattern for, when you retrieve a certain chunk, you bubble up that citation often through metadata.
Yeah, that's exactly. we usually do it. And you can also, yeah, you can add a bunch of any kind of metadata you want to each individual chunk. And then once you retrieve that, then you can basically do a lot of, there's a lot of power in storing your values in metadata and then retrieving them for later use. So next I'm going to go over embedding. And embedding, we basically have, this example just shows how like different embedding models work. So like certain embedding models, well, basically embedding in general is just taking those chunks that we created before, or taking text and then converting them into dimensional vectors, and that we can then upsert into our vector DB. So like Shane said before, we take these our models can turn these into embeddings that allow us to do semantic searches on, or cosine similarity on, to retrieve data when we query our knowledge base. Um, so I'll show some examples of certain embedding models. Um, we have the first one, which is OpenAI Text Embedding 3 Small, which is the fastest. It's the smallest amount of dimensions, so that helps you get it helps you get a good um, speed versus quality in terms of like you want to embed and retrieve your embeddings pretty easily, but you still get a good amount of data stored inside that dimensional vector. Um, then we have text embedding 3 large. Now this is a lot more data can be stored in these vectors, um, but at the cost of it'll take a lot longer to retrieve them in your operations. But they have a lot more value, and they have a lot because of their larger size. They're able to store a lot more details about whatever text or documents you decide to upsert. And then we have here the Cohere Embed English V3, which is this multilingual support. So there's a lot of different embedding models you can choose from. It's not just these three. You can basically, if there is an embedding model that's supported, you have a lot of leeway to choose the right embedding model for yourself. And I can actually show you how what kind of what embedding looks like in action. I just run this example. So I can so basically for this text, the quick brown fox jumps over the lazy dog, you can see exactly what kind of embeddings get created. We're not going to show the whole thing because each the length of each embedding will be like, so the first one will be 1536. That's 1536 values in this array. But we're going to show you the example of like what kind of values are in each embedding. So here's the first five values of like an OpenAI text embedding 3 small. Here's a value for the text embedding 3 large, and then some from Cohere models. Um, yeah, and then various models just let you um, uh, yeah, I think picking the right model is very based on just trial and error, just seeing what works best for your use case. So I think any of these three could be very useful, and depending on what purpose you're trying to use them for. I think that's the embedding example. So we go to the next one, which is the upserting example. So once you have your documents chunked, and once they're embedded, or once you make embeddings from them, then you can upsert them into your vector DB. So I can show that off right now. Let me just go over the example first. So we have a document where that's a vector database guide. It's a markdown file. We have an introduction. We have some other key features right there, and we also just have metadata on that we're going to use later when we upsert. So we have two different documents. We have this one, and we have a search implementation guide, and then we store some more metadata. So for each document, we will use a strategy of markdown. We will split based on the headers, and then once those are chunked, we'll get those documents back. We'll embed them with our embedding model. Then we'll get a vector DB. So in this example, we're going to use a PG vector, which is a very good vector database model to just play around with and do these examples. Um, in our example, I delete the index if it exists. That's just for the example. You don't necessarily need to do that. Um, but you can create an index. So whenever you whatever dimension you decide to embed with, or whatever embedding model you decide to use, you need to make sure that the dimension of your index matches that. Otherwise, if there's a mismatch, you'll have some errors. So we know that OpenAI embedding, the text embedding 3 small is a dimension of 1536. So we're going to use the same dimension there. And then we decide to upsert. We create an index called search examples, and then we decide to upsert all the embeddings into the search examples index. Um, and also include the chunk metadata and the text of the chunk. And then we can see that it successfully upserts these embeddings. So I can run these and show it in action. So when we upsert this, you can see we successfully upserted 4 embeddings. And I can also show you this is just a DB viewer for this. I can show you that these embeddings got upserted. So you see the vector ID, you see each embedding, which is a very long array. And then we see the different metadata that gets added. So we store the text of the chunk. We have different types. So we have the documentation type. We have the source it came from. We have the section we added as a metadata. And then we have the headers. So so looking at this chunk, you can see, oh, this came from the vector database guide and the introduction. So we can go back and you can see that, oh, yeah, it's coming from here. Um, And this is a basic example, but it just shows how powerful it is to be able to just chunk, embed, and upsert pretty easily. And this really was just, well, for me, it was one command for me, or one script to get that done. Next one is after you upsert, you can do a couple of things. And you could even, if you decide that you upserted something, but you wanted to delete a vector or update a vector, after the fact. You can also do that. So in this example, I have 2 documents. One is like a document about cats with some metadata, and then I have a document about dogs with some more metadata. So in this example, I do the same thing I did before. I chunk it with a markdown strategy, get the chunks, I embed them, I get the vector that I want to store them in, or the vector DB. I create an index, I upsert them. So that's basically the same as the last example, but I can afterwards I can get the vectors I want to modify. So in this case, I'm getting all the vectors I can that I just upserted, and then I take a random vector. So I'll take this first cat vector, and then I'll update the text in the for that embedding, and then I will just update that vector, and I'll show you that right now. Let me update delete. Let it run through. Okay, so going through the code, we upload 2 embeddings, upserted 2 embeddings. We get all the vectors after upsert. So you see that in the vector embeddings, we have an ID, we have a score, and then we have all the metadata. So this is a document about cats. We have the type, the source, the section, and then this is a document about dogs, type, source, section. Now, in our example, we take that first vector object, and then we can update it. So we can update the metadata right here. So we actually re-embed the text, and then we update the metadata text in here. So we can see after we update that we change the metadata text from this is a document about cats to this is the updated document about cats now with more info. So you're able to do this with any kind of metadata you have after you upsert. If you decide you want a vector to have more metadata, or if you want to change the vector embedding itself, you're able to update the vector. after the fact and add those details in. Um, and then you can, in addition to that, you can also delete a vector. So say you have add a bunch of vectors, but you want to get rid of a few. Um, you can then query, or you can get a vector ID from your vector list of vectors, and then you can delete it, and that will remove it from your list of vectors. So as you see here, we removed that document, and now we only have the one vector for this is a document about dogs. So that's a good example for that. Next one is now that we've done that part, we can go see how vector search works. So this is probably the most important part, or one of the most important parts, is just seeing how vector search works. So we can, now that we have things in the vector, so we have search examples, which let me change that a bit, make that match up. Little typo there. Okay. Now that we have vectors in the DB for search examples, we can just query the DB now and get some details back. So let me go ahead and run that. Okay. So my first query was, what are the main features of vector databases? And now we get some chunks back related to that. So we did a semantic search based on the vectors themselves, and we were able to get back this amount of data. So so like we get like vector databases or specialized databases that store and index high dimensional vectors for similarity search. And then we have some more data for like there's different pieces from our markdown file that we were able to return. Um, and if we go down here, we can see a vector, an example of vector search with a filter, um, which is like we ask how to implement vector search, but this time we have a filter on implementation. So we check for sections related to implementation, and we can see that we get a more focused search because we're able to filter down the results we get from the vector DB um, and return the right amount of results we want. I think someone has a
Yeah.
question. Should we
Yeah,
answer
so
that
a
right now?
couple
Okay.
questions.
Okay.
So first one, once everything is set up, how do you properly evaluate? I'm assuming they're asking around evaluating if it's the search results are correct. How do you ensure, the agent tools converge and stuff?
For that, there's a couple of ways to evaluate. I think you could use evals to make sure that the agent is properly returning data you have and not hallucinating. Um, I think there's that, and you can also just it's important to know that like I guess human eyes, human evaluation as well will help to determine whether the uh, the RAG is working properly.
Yeah, I mean, I've seen a lot of people, you have a data set of searches and you want to see certain chunks, right? So you kind of curate what you expect to see, and then you can use evals to make sure that you're actually, when this search comes in, you're expecting these things to be retrieved, and then you build that larger data set over time and you try to measure the accuracy to make sure that, as you're changing things and improving things, your data set and your tests still pass or still, give you a high level of accuracy. There's a couple other questions, quite a few actually. One is, can I target pinecone from Mastra get vector? Can you use
Uh,
pinecone, Nick?
yeah, we have we support Pinecone as one of our vector databases, so you can definitely use that.
Yeah. All right. And this one is maybe a little bit more nuanced and complex. Is it particularly helpful to include embeddings for the root or source documents in addition to the delimited chunks, contingent on if it fits within the supported size for the model? I guess, and as a clarification, while everything may not be well represented within the limited vector space, it may be useful for top-down searches. So I, if I'm understanding it, I don't know if Nicholas is asking if you can basically embed the entire root or source document in addition to the chunks, and if that would be helpful. I haven't
Uh,
really seen examples of that being particularly helpful, but I guess I don't know. What do you think, Nick?
you can. There are some vector DBs that actually support that, like out the gate. Chroma is one of them. If you guys know what Chroma is, there is a way to upsert the straight up documents, like your source documents, in addition to chunks, and they offer the ability to filter on the documents themselves. Uh, there's not much outside of that. I haven't seen much where you can where there's a lot of support for that. I think a lot of vector DBs make the assumption that you're going to be chunking and filtering based on that rather than upsetting the whole document. Um, but I would recommend definitely checking out Chroma if you're looking for something similar and you want to be able to filter on documents or work with whole documents.
All right, so we have a couple other questions. How does the search filter work? Is that using the markdown chunk metadata?
Yeah, so right now the filter in our query, these are all it's really a metadata filter. So whatever metadata you add um, to your documents, it will show up as you'll that's how you filter basically. So like basically the metadata right here, you have like source type section and like source type section. So that's basically once those are added to your chunks as metadata, then you can use that to filter. That's the most optimal way to filter right now.
All right, so a few more. I can see how this works great for docs where structure matches expectations, like Markdown, heading one, heading two. But what approaches would you suggest for PDF docs that might be created with 3 to 5 varying formats for sections or subsections?
PDF is an interesting one. There's not a really um, just in terms of handling PDF files, there's not a very like one way to go for that. It's a lot of it is just like converting it to a different kind of file type and then working with that. But if you were working with multiple different sections, you can add for Markdown at least. You can add like a bunch of you can add as many headers as you want, and then set it up in such a way where that even if it's varying formats, you can have it set up so there is a logical progression between different headers.
Yeah,
So it's not just what we have in the example is just 3 headers, but you can add more than that and add more formats than just that.
yeah. And a lot of times I see people, they use some kind of OCR model on the PDFs to get it to convert it into more standardized text. So they have a whole pipeline, right? You take the PDF, use some kind of OCR, get text out of it, and then you use some kind of chunking strategy. And it is hard though, because you're right, like sometimes PDFs have tables and they have all these different things, images, and that is one of the challenges with you know, doing this. And so there's different methods I've seen people, they take if there's an image, you send that through a model and they convert it to like a text representation of that image and that becomes part of the chunk. I mean, it gets pretty complex. It is possible but there's different strategies that probably, depending on the types of PDFs, would lead to different results, I think. Okay. We're getting a lot of good questions, which is good. Do you get help from Cascade and Windsurf? And if so, is there a best model for RAG implementation? I don't know how you determine best here.
Um, I'm using let's see, the best model for RAG implementation. The
And,
best
and I
model
don't
is
I don't know if
Embed.
model is referring to, I'm assuming the LLM that you're using with RAG, or
Yeah,
maybe it's the embedding model. I'm not exactly sure. So maybe we might need a little more information on that.
yeah. 'Cause I think it really is up to if it's best LLM model, or I mean, best embedding model is really determined by your use case. The best LLM model, a lot of them do rank pretty well, like a lot of the major ones. So you can really pick your pick. But I'm not sure if there's really best one. It really depends on your situation. If that's the what you were trying to go for in your
And
question.
then, and I think I maybe kind of alluded to this, but Ryan maybe beat me to it. Can we use the OpenAI responses API like the file search tool and multimodal embeddings to also embed images?
Yeah, you can. That's you can definitely open air responses. You can use that for you should be able to use this for that as well. I should have probably made an example for that, maybe for
Yeah.
next workshop. But
Yeah.
yeah, you can definitely use the responses model.
And then another, just this is more of a recommendation. I can recommend trying contextual RAG where you include AI generated context from the whole document together with the chunk. So that's kind of a cool idea.
Yeah,
Um,
it's a good example too.
and
Yeah,
then
I should write that down.
probably a better pattern to follow bottom up, including metadata to filter against chunks with the same source document. Yep, I agree with that, Nicholas. So for storing and analyzing many user messages to find certain patterns, which chunk strategy would you use? So I'm
Hmm.
not sure where user messages is this in the context of messages to the LLM or if it's messages in some kind of chat interface. I don't know. Any thoughts on that one, Nick?
Currently, okay, in the chat interface, I would say recursive. It's the most because it's more complex than character. Character is not very character is only really good for simple examples. I think recursive will fit your needs a lot better, and it lets you work with a bunch of different types of messages. Because it's hard to say like what kind of context is going to be in each message. So I think recursive helps to do that a little bit better. It's basically our default way to chunk is by doing recursive chunking, just in terms of the kind of context it can save. And I think from there you can tweak it to get exactly the right results you want. So I
All
think
right,
that
so
would be a good strategy to go with.
two more questions and then we're gonna keep moving on because we have about 15 minutes remaining.
Oh,
So this
okay.
one's from YouTube. And I could probably answer this one. What's the equivalent way to use state and state transition in Mastra, similar to lane graph? Workflows question mark. And then yes, I would say workflows is the way to do that. So if you're looking for how to do similar things to lane graph work, you can use workflows and you can kind of pass in context between steps in those workflows. So that I would say that answers that question. Good question though. And then last one before we move on, do vector DBs offer a way to find clusters of related items without a search term? If so, does Mastra offer anything to make a vector DB query like that? I'm not sure if I understand that, but
Well,
maybe you
I
do,
think
Nick.
they want to query because a lot of our queries right now with vector DBs they need a like a query term because the query string gets embedded and that's used for the semantic search. It sounds like they want to be able to do that without requiring a search term. Um, that's something we don't offer just yet, but that is something that people have been interested in. So it's something we're going to look into. Um, but currently, we don't have we don't offer a way to query without a query string.
Cool. All right, we can keep going. We have about 14 minutes left.
Okay, I'll try to go quick so we get to the workflow example. Um, so this example is, oops, let me just change my things real quick. Cool. So this example is very similar to the vector search example, except this one involves re-ranking. So what that means is we'll query based on this query string. We'll get some results back. We'll get some initial search results, and then we can re-rank those results using our Mastra re-rank function and including a re-ranking model. So in this case, we're using Cohere re-rank 3.5. So I can run this example right now. Let's just show you these results. So we have initial search results, and each vector gets a score based on how semantically similar it is to the query result. So here we have a score of 0.63, and then we have like a certain chunk right here, or some metadata explaining what the vector is. We have another one, 0.55, and then another one that's 0.49. So and another one 0.45. So we have these results, and we can re-rank them by passing in the results again and including a re-ranking model. So we have Cohere re-rank 3.5, which is just for re-ranking. And we get back some results. So we get back the original result, but we add on additional data to that. So we have a new score. Our old score was 0.63, but our new score is 0.59. And we have details for exactly why you got that score. So we have like semantic was 0.36, so it wasn't very semantically similar, but the vector score was a lot higher. So like the vector data was a lot more closely together. And then we have a position score. So the position score is basically where it was in the initial ranking list. So we used all those three scores and put together to come up with a new score of 0.59. So that's basically how it works for each one of these different results, where we combine the semantic similarity of the like metadata or the re-ranked query, the vector, and then the position to come up with a new score that changes where it is in the new list. So then we have this one. We have to get a top K of 3 just to get some values here. And this basically lets us get, if we have a lot of initial values, we can then use this re-ranking just to determine we don't want, we get a lot of values that might not be entirely relevant to our query. So then we can just use this to get more focused results. So now that that's done, I can now show off just some, I can now show off the like some basic search tools in our playground. So let me first do this. Let me upsert some documents. So I'll show you the upsert script real quick. So um, we have this script that just takes in different documents that we have in this folder. So here we have an applications JSON folder. We have an auth markdown folder just explaining about a random authentication system. We have one for error handling, and then we have one for logging that explains how logging works. Now we upsert each of these different documents. So we have a bunch of markdown documents that we upload, and then we have that JSON configuration file we upload, and then we chunk them based on the different different chunking strategies. So the markdown files will be chunked with the markdown strategy, split by headers, and then we add some sizes to that markdown file. And then we do the same for the chunking strategies or the JSON chunks. We add a JSON strategy. Then we just upload that into a vector DB under the workshop index. So let me show that off. So we've successfully uploaded 28 document chunks that we can now use when we use the playground. So I can do that right now. Let me start this up and then it should go over here. Cool. So the first thing, I'm going to show the code first before I go to the example. So the first thing we're going to do is we're going to try using the basic agent. The basic agent is it's a Mastra agent. So it's a very basic agent. It says helps explore and understand code bases using RAG. We have a GPT-4o as a model, and then we have this is the important part is the basic search tool. So this is the basic search tool that we're going to use that the agent is going to use to search through the knowledge base. Now, this is a pretty basic tool for RAG. It's a it gets an input schema of a query and gets a limit which defaults to 5. Using that, we'll get like our vector store, and then we'll embed our query, and then query that using our limit and our query vector, and get some results back that the agent can use. So let me move this over here. Okay, so the first thing I'll ask the based on what we have in our knowledge base, the first thing I'll ask our basic agent is like, how do we implement JWT auth, oops, auth, in our system. So it's running the basic search tool. And let me show you this real quick. So we have two arguments. There's of query. It's GW auth implementation from our query, and then a limit of 5. So we get some tool results back, and then we can see that the agent took from our knowledge base, from our documents, and gave us a response accordingly, and gave us a sample implementation as well. Um, and we can do that for another, let's ask another question. We do our standard error handling patterns. So now we can see that in the results, we can see that it's like the same tool arguments, and we get some results back. And we can see that it got again from our knowledge base and provide us a response. So that's our basic search tool. Now the next search tool I want to show real quick is our query vector agent. So this is very similar to the basic agent, except we use something called the query vector tool. And that's a tool that's provided by Mastra, so you can easily set up a tool to query vector databases. So all you need to do is provide like a vector store name, which is the whatever vector store you're using, the index, the model, and then some other relevant data, like if you want filters enabled and we want re-ranking. So I can show this one off as well. Um, so let me go to agents. We go to query, and we go to query vector agent. And here I can show off I'll just take a copy paste from here. Like there, I can show like ask it a question called like find implementations in our code base that show how we handle database errors and validation errors. So I can ask it that question. And we can see that it gets details from our database just related to database and validation errors. But we can look inside our vector tool arguments, and you can see that it also added in the top K value, so that's the amount of results we want to return, as well as a filter value. So we can see that we want error handling, so it'll search in sections related to error handling to give us our values. So this is just an example, one example of what we can do with the vector query tool, and how we get data from there. So that's pretty powerful, and it's pretty powerful to be able to have several a simple tool that lets you add filters or re-rank and provide data like that in that way. And you won't have to create a tool from scratch for that. The last, like we have 5 minutes left. So the
We have five
last,
minutes.
yeah, I'll go real quick on this. So the last thing I want to show off is our show how to use RAG within a workflow. So this would be a very basic example. And if you don't know much about workflows, you should still be able to follow along. It's very simple. It's pretty simple. The first thing we do is we create a step for getting some markdown file from a URL. So we can add a something called fetch raw markdown step that gets us the markdown text. Then we can chunk it in our chunk markdown step. So we just take that text data we got from the previous step, we create a markdown document, and then we chunk based on with the chunk the markdown strategy, and then return the chunks that we created. And then in the next step, we're able to embed those chunks and then upsert them into our vector database. So very similar to what we've seen before, except this time it's in a workflow flow. So we can see like we can like add in a URL and we get back some text. And these are the various steps we have to chunk, embed, upsert. So I can show that off right now. So let me take the example we have in here. Whoops. Okay. So I can add this one. Could run this. And right now it fetched the raw markdown, it chunked it, and now we embedded it. So I can open up our execution. And you can see that at the end result is that we have a bunch of chunks that we just added to our turret vector DB. And I can show you real quickly. I can just go to, I have an agent that will query this vector DB for this index and provide me um, results from them. So I can do like, give me a random story. Let's see here. Give me a random story. Then now we have something, a story search tool. And this will get me a relevant context from the stories we just upserted from Aesop's Fables. And yeah, so now we can see a random story from that book. So this is a pretty powerful way to easily just embed and chunk embed and upsert, and then you can use it uh, in your agent uh, to get your results.
Very cool. And one quick question, what's the best strategy for HTML? In this case, it was a markdown in a file, but what if it was HTML?
We actually do have HTML strategies as well. So we have a strategy just for that. So you can use that strategy for chunking HTML files.
Awesome. Thanks, Nick. We have about 1 or 2 minutes left, so we'll just wrap up really quickly here. Thanks everyone that has tuned in. Hopefully you've all learned quite a bit. I guess, Nick, if you want to drop we have this available in a public repo, right?
Yeah,
Okay.
I'll share a link in the chat.
Yeah, so if you want to share a link and then I can just share some ending slides here. So please check out the link if you do want to see a little bit more of the actual code that we went through today. And with that, let's wrap up. Okay, so we just went through all of these things. Please give us a star on GitHub. You can, check out the website. If you do have more questions, drop into our Discord. We have, a lot of people from the team are in there. Obviously, we have a really great community as well that tries to help out. We're going to have more workshops being announced today. So we don't have any on there right now, but there is one next week. And it's going to be on agent networks, which is a cool new thing that we want to talk about. And it's going to be great. So please subscribe to our calendar or join that event as well. You can connect with Nick and myself on X. And then, yeah, as I mentioned, please give us a star on GitHub. That helps more people find out about Mastra. If you want to try out Mastra Cloud, if you're building agents and workflows and you want to deploy that somewhere, you can go and sign up for our cloud beta. And with that, thanks everyone for tuning in. We appreciate it. And we hope to see you all in an event soon. See you, everybody.
Bye, everybody.